All right, let's dive right in. Today, we're going to demystify one of the most fundamental tools in all of control engineering, the PID controller. Seriously, if you've ever wondered how things like your car's cruise control or even massive industrial robots maintain such incredible precision, well, you've come to the right place. We are going to break down not just how they work, but the real art form, how to tune them.
So here's our roadmap. We'll kick things off with the absolute basics. What exactly is a PID controller? Then we'll get into the real heart of the matter, the challenge of tuning. From there, we'll look at a couple of ways to tackle it. First, a hands-on, intuitive manual method, and then the more systematic, formula-driven Ziegler-Nichols methods. And to wrap it all up, we'll talk about where these tools actually fit into the bigger picture of real-world engineering.
Okay, first things first. What are we even talking about when we say PID controller? Let's lay that three-term foundation.
At its core, you can think of a PID controller as a really smart thermostat. It's constantly looking at the error, that's the gap between what you want to happen and what's actually happening. Its entire reason for being is to make that error as close to zero as possible. The real magic, though, is in how it does that. It uses three different strategies: proportional, integral, and derivative.
Now, I know this might look a little intimidating, but this single line of math basically captures the controller's entire brain. It's called a transfer function. Don't worry about the S for now. In control theory, it's just a tool for analyzing systems that change over time. The key thing to see here is that 1 over S represents integration, like summing things up, and S represents differentiation, or the rate of change. All this equation is really saying is that the controller's output is just the sum of these three separate actions. That's it.
Let's break those three down. The proportional term, Kp, is all about the present. It looks at the error right now and reacts proportionally. Bigger error, bigger reaction. Simple. The integral term, Ki, is the historian. It looks at the past, adding up all the little errors over time. This is fantastic for getting rid of that tiny nagging error that the proportional term might just give up on. And finally, you have the derivative term, Kd. This one's the fortune teller. It looks to the future. It sees how fast the error is changing and applies the brakes to stop the system from overshooting its target. So you've got the present, the past, and the future all working in harmony.
So we have these three amazing tools, right? But their power, their effectiveness, it all comes down to three little values: Kp, Ki, and Kd. And this brings us right to the central challenge of PID control. How in the world do you find those magic numbers to make your system behave just right? This really is the million-dollar question, isn't it? A controller with the wrong settings can make a system sluggish, or worse, wildly unstable. Finding these perfect gain values is a process we call PID tuning, and honestly, it's as much an art as it is a science.
So the most direct way to get started is to just, feel it out. I want you to think about adjusting the knobs in a shower to get the temperature just right. You turn the hot a little, feel the water, turn the cold a little, feel it again. You're doing manual tuning. It's a hands-on, trial-and-error approach.
Okay, this process is a lot more methodical than just fiddling with knobs. Here's the game plan. First, you turn off the integral and derivative gains completely. We want to isolate the main actor here, the proportional term. Second, you slowly, carefully crank up that P gain until the system starts to wobble or oscillate. You're finding the very edge of stability. Third, you back it off from that cliff just a bit to a safer spot. And finally, once that main response is stable, you start to bring in the I and D terms to clean everything up, getting rid of any leftover error and smoothing out the bumps.
And that safer spot we mentioned, it actually has a name: quarter amplitude decay. This is our target. It's a classic engineering compromise, you know? It makes sure the system settles down quickly without being so aggressive that it flies past the target. We're aiming for each little wobble or oscillation to be just a quarter of the size of the one before it. It gives us a really tangible goal to shoot for during our manual tuning.
Now, manual tuning is great, and it gives you a real feel for the system, but it can take a lot of time, and it really depends on the operator's experience. So for a more systematic, repeatable approach, engineers developed the Ziegler-Nichols methods. These basically give us a recipe book, formulas to calculate the gains.
And there are two main flavors. The first is the closed-loop method. You do this with the controller still running. It's live. You actually push the system right to the edge of instability to see how it behaves. Yeah, it can be a little risky on a live system, but it gives you a super accurate picture of its real dynamics. The other way is the open-loop method. This one's much safer. You take the controller offline and just give the system a little kick, a step input, and you watch how it naturally reacts on its own.
For that closed-loop method, we're on the hunt for two critical numbers. First up is the ultimate gain, or Ku. This is the exact gain value that makes the system oscillate forever, without the wobbles getting bigger or smaller. It's the tipping point. The second is the ultimate period, Pu, and that's just the time it takes for one of those perfect, sustained oscillations to happen.
And this table, this is where the magic happens. Once you've gone through the work of finding your two special numbers, Ku and Pu, you just plug them into these formulas. And look at this. For a full PID controller, your starting proportional gain, Kp, is just 60% of that ultimate gain you found. Your integral gain, Ki, depends on both Ku and how fast the system was oscillating. It makes perfect sense. It's an amazing recipe that turns real experimental data into a solid set of starting numbers.
To make this less abstract, let's grab the numbers from the example in our source material. They did the test and found that for their particular system, the ultimate gain, Ku, was 885.5, and the ultimate period, Pu, was about 0.8355 seconds. So now, we just apply the recipe from our table. For a PID controller, we take that ultimate gain of 885.5, we multiply it by 0.6, and boom! It gives us a starting Kp value of 531.30. No guesswork. We just do the same thing for the other formulas in the table to get our starting Ki and Kd values too. Okay, now let's switch gears to that other Ziegler-Nichols approach, the safer open-loop method. Instead of pushing the system to its limit, we just give it one nudge and watch what happens. Think of it like tapping a bowling ball. We're measuring two things here. First, how long it takes before it really starts to move. That's our transport delay, or delta t. And second, how quickly it picks up speed once it gets going. That's our reaction rate, or R.
And you guessed it, we've got another recipe book. Once you've measured your system's natural delay and reaction rate, you plug them right into this table. And check this out. If you have a system with a really long delay and a slow reaction, that R times delta t value is going to be big, which means your proportional gain will be smaller. The formula is basically telling us, hey, be more gentle with this sluggish system. It's a different set of measurements, but it gets us to the same place, a really solid set of starting gains. Now, after seeing these powerful, formula-based methods, it would be so easy to think that we've found some kind of magic bullet for tuning, but it's really, really important to understand where they fit in the actual design process. This quote from the source material absolutely nails it. These methods give you excellent candidate gains. They are a phenomenal first step. They get you 90% of the way there. But they are based on a simplified model of reality. And in the real world, you'll almost always need to do a little bit of final manual tweaking to get the absolute best performance.
And this really leaves us with a question that gets to the very core of what it means to be an engineer. These formulas can give you a really solid, good enough answer in minutes. Chasing that theoretically perfect tune could take you days of tweaking. So the question we all have to face is, in a world of deadlines and budgets, when is a fast, structured formula the smarter tool than a perfect solution that you might never even reach? Thanks for joining this explainer.